Welcome to my channel. Please subscribe. SMQTT. Secure Message Queuing Telemetry Transport, or SMQTT, is a secure version of the Message Queuing Telemetry Transport (MQTT) protocol. MQTT is a messaging protocol that is commonly used in Internet of Things (IoT) applications to enable communication between devices. However, MQTT is not inherently secure and can be vulnerable to attacks such as eavesdropping and man-in-the-middle attacks. SMQTT addresses these security concerns by adding encryption and authentication features. One of the key features of SMQTT is its use of Transport Layer Security (TLS) to provide encryption for data in transit. TLS is a protocol that is widely used to secure communication over the Internet, and is commonly used to secure HTTPS connections. By using TLS, SMQTT can ensure that data is encrypted before it is transmitted, preventing eavesdropping and other attacks. SMQTT also supports mutual authentication, which requires both the client and the server to authenticate each other before communication can take place. In addition to TLS, SMQTT also adds support for message-level encryption using the Advanced Encryption Standard (AES). With message-level encryption, data is encrypted at the message level, providing an additional layer of security on top of the transport-level encryption provided by TLS. This helps to protect against attacks that may occur during the transmission of individual messages, such as replay attacks or message tampering. SMQTT also includes support for access control and authorization, which allows administrators to control which devices are allowed to access the system and what actions they are allowed to perform. This can be especially important in IoT applications, where devices may have different levels of access to sensitive data or control over critical systems. By using access control and authorization, administrators can ensure that only authorized devices are able to access the system, reducing the risk of unauthorized access or data breaches. In summary, SMQTT is a secure version of the MQTT protocol that adds encryption, authentication, access control, and authorization features. By using SMQTT, IoT applications can ensure that data is transmitted securely and that only authorized devices are able to access the system. With its combination of transport-level encryption, message-level encryption, and access control features, SMQTT is an important tool for securing IoT applications and protecting sensitive data. CoAP. CoAP, or Constrained Application Protocol, is a specialized web transfer protocol that is designed to handle the communication between IoT devices in constrained environments. Constrained environments refer to low-power, low-bandwidth networks where devices with limited memory and processing capabilities operate. CoAP is designed to minimize network overhead, provide reliable communication, and ensure efficient use of resources. It uses UDP for transport and can be implemented on top of IPv6 or IPv4 networks. CoAP supports several methods for communication, such as GET, POST, PUT, and DELETE. GET is used to retrieve data from the server, while POST is used to send data to the server for processing. PUT is used to update a resource, and DELETE is used to remove a resource. CoAP also supports Observe method that enables IoT devices to subscribe to a resource and get notified when it is updated. CoAP consists of several components, such as endpoint, message, request, response, resource, and observe. An endpoint represents an IoT device that can send and receive CoAP messages. A message is a CoAP packet that contains a request or response. A request is a message sent by an endpoint to retrieve, update or delete a resource, while a response is a message sent by the server to respond to a request. A resource is a piece of data that can be accessed by an endpoint using URI. Observe is a CoAP feature that allows endpoints to subscribe to a resource and receive notifications when the resource changes. CoAP is widely used in IoT applications that require low power and low bandwidth communication, such as smart homes, industrial automation, and energy management. For example, in a smart home, CoAP can be used to control and monitor IoT devices, such as lights, thermostats, and security systems. In industrial automation, CoAP can be used to monitor sensors and control actuators in real time. In energy management, CoAP can be used to monitor energy consumption and optimize energy usage. CoAP message types. Constrained Application Protocol (CoAP) is a protocol designed for resource-constrained devices and low-power networks, and it is widely used in the IoT ecosystem. CoAP uses a simple request-response model to communicate between clients and servers, with a focus on efficient data transmission and low overhead. One of the important features of CoAP is its support for message types, which are used to specify the nature and purpose of a message. There are 4 types of messages in CoAP: confirmable, non-confirmable, acknowledgement, and reset. Confirmable messages require a response from the receiver, and the sender will retransmit the message until a response is received. Non-confirmable messages do not require a response and are used for one-time events. Acknowledgement messages are sent in response to confirmable messages to confirm receipt, while reset messages are used to cancel or reject messages. The use of message types allows CoAP to provide reliable and efficient communication in low-power and resource-constrained networks. Confirmable messages play an important role in CoAP communication by ensuring reliable delivery of messages. When a confirmable message is sent, the receiver must acknowledge the message by sending an acknowledgement message. If the sender does not receive an acknowledgement message within a certain time frame, it will retransmit the confirmable message. This process is repeated until the sender receives an acknowledgement message, ensuring that the message is delivered reliably. Non-confirmable messages are used for one-time events, such as requesting the current value of a resource. Since non-confirmable messages do not require a response, they do not incur the overhead of confirmable messages, making them more efficient for one-time requests. Acknowledgement messages are sent in response to confirmable messages to confirm receipt. When a confirmable message is received, the receiver sends an acknowledgement message to the sender. The sender waits for the acknowledgement message before sending any subsequent messages, ensuring that messages are delivered in the correct order and reliably. Reset messages are used to cancel or reject messages. When a reset message is received, the receiver cancels the message and does not send an acknowledgement message. This allows the sender to know that the message was not received and take appropriate action, such as resending the message or canceling the transaction. In conclusion, CoAP message types are an important feature of the protocol that allow for efficient and reliable communication in resource-constrained networks. By using confirmable messages for reliable delivery and non-confirmable messages for one-time requests, CoAP provides a flexible and efficient communication mechanism for IoT devices. Additionally, acknowledgement and reset messages help to ensure that messages are delivered reliably and in the correct order, further enhancing the reliability of CoAP communication. CoAP Request Response Model. CoAP, Constrained Application Protocol, is a protocol designed to enable communication between devices with limited processing power and memory, which makes it well suited for IoT devices. CoAP uses a request-response model to exchange messages between client and server. The client sends a request message to the server, which then sends a response message back to the client. The request message typically includes a method, get, post, put, delete, URI, and optional payload. The response message includes a status code, a payload, and optional metadata. The request-response model in CoAP is similar to the model used in HTTP, but CoAP has been optimized for source-constrained devices. The messages exchanged in CoAP are also smaller than in HTTP, which reduces the amount of data transmitted and reduces the processing requirements for devices. The request-response model is used in a variety of applications for IoT devices, including smart homes, industrial automation, and transportation. For example, in a smart home application, a user might use a smartphone app to send a request message to a CoAP server in their home, which would turn on the lights in a particular room. The server would then send a response message back to the smartphone app to confirm that the lights have been turned on.